for Get Together. Today we are going to talk about NFTs and nftables, formerly known as X-tables. So I'm Jasper Wiegratz from SVA. SVA is a German system integrator. So at Day, what I do is OpenShift. I'm solution architect for OpenShift. Started with Docker in 2015, and then Kubernetes came, and eventually I got stuck with OpenShift 4. And also I always do Ansible. I try to not leave any project without leaving at least an Ansible playbook. So in the masters, I had a lot to do with Linux networking and with container security. I was in a one-year project where we built a home network security solution for basically OpenWRT routers that I will show you a little bit about. We worked completely in Rust. I would have not dared to delve into Rust on my own, but I was forced to, and in hindsight, I'm extremely grateful for that. So who in here is also using Rust or would call themselves a Rustacean? One hand, okay, great. Also, I have to say the meaning of Rustacean is simply a person who is using Rust, and by no means it means that, for example, I would be a demigod and I still need to learn a lot, but it's been 3 or 4 solid years of using Rust, and I experienced that my contributors are often more knowledgeable about a few of those hardcore Rust techniques. So what are we going to talk about today? First, a little bit of context. I will show you something from the project at university, a solid use case to use nftables. We will explain, we will see how IP tables worked and the other kinds of X tables there were and how they map to nftables. Then how to automate that. With this example, how to automate in Rust, but you could just transfer this to any other programming language as well, and the challenges that I faced in automating nftables. I will show you this SDK that I created for nftables, and we look at all the lessons that I learned. I will share with you and what would be next in this universe of using nftables. And then you may ask questions or leave for the get-together. Okay, let's look at this project. So there's a standard called MUD, Manufacturer Usage Description, and it was created by Cisco because they wanted to solve a problem in home networks. So in the reality in home networks, imagine your home, your mom's home maybe, there is probably simply one single Wi-Fi network or wired network. Everything's in that single domain. Maybe there's a guest network, but that's about it. You will have multiple smart dishwashers, smart washing machines, fans, smart TVs, whatever. So these devices can be compromised. They have old firmware. So it would be great if it wasn't just that everything had unrestricted access to the internet and not unrestricted local access. You don't want your outdated smart TV talking to your fans, for example. Bad things could happen. So what would be the cure for that? In enterprise networks, we have something called microsegmentation, and ideally, microsegmentation comes with something more than an any rule and with something like tailored access policies. Now, the typical homeowner would not be qualified to create firewall rules. So this is why this is very far from reality. So the idea behind MUD, the manufacturer usage description, is what if every smart device would have a tag to it, a metadata description that it announces. So technically this is implemented when a smart device registers to the network by sending a DHCP request. They would send a link to a JSON file that would contain, as a manifest, contain all the network communication information. For example, an Amazon Alexa would say, I'm an Amazon device and I want to talk to all other kinds of Amazon devices because we have a common protocol, and I also want to talk to Philips smart devices. That could be some kind of access rule. And also I want to talk to the voice recognition server of Amazon at AWS and another update server. So that could be a rule set. So we implemented this MUD standard in the NAMIP project. This is short for Network Access Makes Internet Better. And we did so by customizing OpenWRT. So we put a Rust-based enforcer component on it that would enforce in the firewall the network access policies that are well, generated from all of the devices that we have. Because if we have 5 Amazon devices, a few more from Philips, you would have a network graph that you could then render into concrete firewall rules. So this is the stack that we created. And this is why I had to use nftables, why I had to use Rust, and what I really like about it, I will show you now. So let's look at the old and the new world. Let's take this example here. This would be, like I described, the use case. We have this voice assistant by a manufacturer. It can talk to its own manufacturer's update API. We have smart lights from another vendor. And now you have this relationship here that the assistant can talk to the smart light, but the smart light cannot talk to the voice assistant, right? And both can talk to their respective servers. And they are both obviously in the same Wi-Fi network. So how would we implement these network policies with IP tables? I think most people in here have used IP tables to some capacity in the past. So you are probably very knowledgeable about this kind of rules here. So you know the syntax. We will write to the so-called output chain. We append a rule. You at the 1.150 IP address, you can talk to the destination IP 165. That is assistant to the bulb on a port 9999. And that is an accept action that we take here. Same goes for the voice assistant to the update API in the internet, and all other packets shall be dropped. This could be some rule set. So I added an exclamation mark here in the first rule because it will have no effect. Why is that? Because IP tables will only act on routing, and we do not do routing in the same network. And this is where typical firewalling falls short. This is why we would need microsegmentation. So how can we implement microsegmentation ourselves in a Linux router, for example? We need to go deeper in the stack. We need to go to Ethernet and frames because we are at the switching layer. So we have EB tables for Ethernet, right? So that acts on bridges. So in an OpenWRT home router, for example, you would typically have 4 LAN ports for the local wired network and then another WAN port for the internet access, and you have one or more wireless modems, so to create your Wi-Fi networks. The Wi-Fi and the LAN is typically in a bridge called BR-LAN, LAN bridge. And this bridge is configured to be a switch, basically. Yeah, it will just get packets from the wireless to the LAN and vice versa, and between the LAN ports. So what we can do with EB tables, if we convince the kernel that it should put all the Ethernet frames on the bridge into the kernel, we need this hook. It's disabled by default because it's adding a lot of stress to the router to think about all the Ethernet frames than just offloading it to the hardware, but we can do it. Then we have EB tables. It looks a little bit like IP tables, as in you will have a source and a destination. This is by MAC addresses. And also you can, and this is quite interesting, you can inspect higher protocols. So if on the EB tables you match for the IP ether type, so if the Ethernet frame contains an IP packet, then you can also look at the IP layer, and if you are in the IP layer, you can also look at is it a TCP packet, and then you could match on a port. So you can move upwards from Ethernet to IP layer to TCP UDP layer. And in this case, we would have a rule that is assistant to LAMP from this MAC address of the assistant to the LAMP MAC address, and accept this and drop all other frames. This would be very brutal on your network if this was a rule, because then only this kind of communication could take place. But these are the building blocks we have. So EB tables has a very similar syntax compared to IP tables, but it's not the same. So you would need to learn more about EB tables. So nftables came here to solve this. So we have a one framework to rule them all, one API, one syntax. And this is the example of the IP tables rules. in nftables. So you have a filter table. You can have multiple tables, just like in IP tables. It's like a namespace for your firewall. They can coexist. And then in this case, we have the output chain with the policy drop, which means drop all by default. So we don't even need this drop statement in the end that we had in IP tables. And we have a slightly changed syntax here, but it still makes sense compared to IP tables. Now note, this is a structured document. This is not with -j-a anymore. So it's a declarative API. And very much same syntax for the Ethernet or bridging example to restrict the local access. So you see here either source address from there to the destination address, and we accept all that is on IP protocol TCP, and the TCP destination port is 9999. So we also switched up we introspected into higher protocols from here. So to compare both, X-tables, or which is IP tables, for example, is very old. 2001 we had IP chains. And X-tables consists of, the X stands for IP tables, IP6 tables, ARP, so you can also use this tool set on ARP, and EB tables for the bridging. And also what is missing here is IP sets. So you could use that, for example, to block all the IP addresses on the internet that belong to twitter.com, that you would put that into an IP set. This is also one of the X-tables tools. In nftables, you have just nftables, and it can speak with all of those families instead of having different commands, different implementations here. So X-tables was always imperative, as I showed. It's commands to add to a chain, and I think this is not very intuitive because you add something with IP tables, and then you look at the table. This is not as nice as having a declarative document that is formatted in, well, JSON-like structure. Yep, and as I said, the schema in X-tables is different per family. It's very specific, and you would have one schema, one unified syntax to rule all of those families in nftables. As for persistence, this is not really native to either of those. So in X-tables, you would typically have a systemd service that will use IP tables restore to load, well, basically a list of IP tables commands from a file, and you would use IP table save to put your current firewall configuration into this kind of file. In nftables, you have this file syntax. So, for example, you have the etc nftables.conf, or on RHEL systems, it's etc sysconfig nftables.conf, where it's automatically loaded from. So, okay, how would we automate this? First off, this is a challenging ecosystem. We have at the lower layer, we have kernel modules. So there was a shift from IP tables to nftables. nftables is the default in Fedora 32 and newer, RHEL 8, Debian 10, and Ubuntu 21.10. So you are probably using nftables if you are using a modern Linux system. So there was a shift here, and we used to have the IP tables kernel module. This is on the right. In these newer versions of Linux distributions on here, this was replaced by the nftables module. Still, you have the IP tables command. How does it work? It's a shim that will forward your IP tables command and translate it to nftables and talk with the nftables kernel module. And now there's more in the higher layer of the stack. So you don't just use nftables and IP tables, you also have something like Firewall D, which will integrate with either of IP tables or nftables. And above that, you would have probably something like Podman or Docker on your system. They also interact with your nftables or IP tables system. Docker will always go to IP tables. They could probably go further and integrate with nftables nowadays, because nftables is already established and old. Or if you look at Podman, they have Netherwark. So Netherwark is the network backend configuration layer of Podman, and they integrate with either of those. So Netherwark can use Firewall D, IP tables, or nftables. In fact, it's using nftables by default in Fedora 41. So a few weeks ago, it was they put nftables as the main or default backend for Podman. So if you want to automate, you have to think about conflicts because you don't want to write to a low-level layer that is managed by an upper layer. If you have Firewall D, you would probably want to use Firewall D instead of just writing to IP tables or nftables directly to avoid conflicts. So how can we automate? So you always have with nftables the files that I talked about. So they would be in one of those places. Depends really on the distribution. In NixOS, for example, you just render it to another place. In dynamic automation options, you have the CLI. So also nftables has the imperative interface with the nft command. I think it's easy to use. It's, for this example here is nft add rule, inet filter, so it goes to the IPv4 and IPv6 table filter and drop all packets that go to TCP port 25. And then there's a JSON API, and I think this is extremely interesting for automation. So you can just pipe a JSON file in a specific schema to nftables, so it has this -j flag, which will enable JSON mode. And you can also use that to output it with nft-j list rule set. You will get the rules as JSON. So JSON API, and I took that because I had the challenge in the MUD project. So the MUD standard by Cisco, it is able to describe almost every kind of firewall configuration that you will have with a Linux system that you can express. So all kinds of TCP options, IP options, and so on. And I needed to make all that accessible from Rust. So I needed to implement an SDK that has all of the capabilities of nftables, and I picked the in Rust, I picked the JSON API of nftables to implement that. So out of that grew this project, nftables RS. Of course, it does require nftables to do something. So basically, you use nftables RS to model a firewall rule set. It will then generate to JSON and apply that to your nftables system. So the benefit here is it's 100% written in Rust, in safe Rust, so I'm not going to unsafe mode. It does not need to be rewritten in any language, and not in Rust, especially because it is already Rust, right? So if anybody wanted to implement something like that in another programming language, which makes sense to interact with nftables, they would have to implement a little bit more than 100 plus types. I think it's easy now because it's quite okay-ish documented. So I think this is complete, but every now and then I get an issue where somebody found a new feature in nftables that is not documented by nftables, and then we fix it and improve our own documentation from this project here. So I'm still working on the documentation here. Okay, how would it look to create an IP-based drop rule for IPv4, like in the previous example? So we write Rust code. We create a batch. The batch is it can be just a complete firewall set, or it can be like delete and add operations. So it can be idempotent or actionable. So the batch would need to respect the schema, which will list, the schema lists either commands or data objects at the very top. It can contain these statements like insert a rule, and you would always use a lot of expressions. For example, the port is a number, port 25, so that is an expression. So this is like building a parser, right? You have these building blocks of the grammar. So the example is we have an add object, an add command object that references a rule object that is continued by a match statement, match to match an IP address, and then drop is the final statement, which is a verdict. So we have this batch containing exactly this rule set. We compile it to JSON with the library, and then just pipe it into nftables, and there we go, we have this rule set active. So let's look at some real world examples. What can we build out of it, or what have people built already out of it? So I mentioned the NAMI project. I have to say this is very, well, academic, so we are not going to expect anybody to use it on their home router anytime soon, also because basically no commercial IoT device, smart device manufacturer implements this standard on their side. So there's, well, you can have this automation framework with NAMIP, but it will not recognize any devices, right? There's simply no policies here, which would be great if there were. So we built this for the microsegmentation. Also, I mentioned Portman. So Portman is using nftables RS as a backend since 2023, and with Fedora 41 and RHEL 10, they are switching to nftables by default. So this is actually the project that I try to cater to make it very usable for Portman. But also there's been a lot more. There's the Pixel Flute servers on the Chaos Communication Congress. Typically, so they put up like a beamer or a pixel wall, and then you can send UDP packets to this server and render a specific pixel to a color. So basically, the more bandwidth you have, the better chances you have to put your picture on there permanently, right? So it will look something like that, images overlaying each other. Bandwidth wins. So you would use nftables in the setup to do rate limiting to specific IP addresses, to block them, to do traffic shaping in a broader sense. And all of these projects are written in Rust, of course. Rust is also a good choice for a Pixel Flute server, it seems, because it's performant. Other people built a blockchain for Web 3.0. An authenticated port knocker that will open your firewall ports only if you send a specific sequence that is not just ports, but also with more data in it. Extremely interesting, and somebody implemented BGP flow spec. Okay, lessons learned from here. So I can really recommend this JSON API over the native API. Before I implemented the JSON API in Rust, I looked at the Malvat VPN implementation of nftables in Rust. They used bindgen, so they were FFI binding to the native library of nftables, and I think they implemented something like 5 or 10% of nftables. Because it's really like reverse engineering nftables to do any progress, to implement more of the features of nftables on the Rust side. So the JSON API on the counter side, it has some kind of documentation. It's easy to work with. So if you're going to work with nftables in another programming language, probably just pick the JSON API. That being said, there's still this JSON schema missing, and I think this needs to be worked on. It would be required to verify the correctness of any implementation that interacts with nftables. But I think from all the work that I put into nftables RS, we can quite simply generate this JSON schema, maybe upstream it. And also I learned that man pages may be incomplete. This is probably true for all kinds of documentation, that they may be outdated. Also, one thing I integrated, I got a tip from some Red Hat engineer that I can improve my testing, my automated tests in the CI by not using sudo for all the tests, but by using rootless testing with net namespaces. So, because if I want to test something, then I need an nftables, which is part of the Linux kernel, so I need a privileged context for that to work. So let's look at this. Actually, I need to go here. Okay, so we are on a Linux system, and we try to look at nftables. It doesn't work from a non-root user. So if I put sudo there, then I can see nftables. So I just, with unshare -rn bash, I went into a network namespace. So I can now, as an unprivileged user in this namespace, interact with nftables directly. So in this case, I'm creating a chain, and I'm giving the same rule. I'm using the same rule I had before. So I'm dropping all to port 25. So this is great. This is something I could integrate. And so if you do research about containers, how do containers work, you will very quickly learn it's with namespaces. And this unshare command you can simply integrate to run something as an unprivileged user in a namespace. And this, for example, can enable you to, well, test the firewall without being root. Okay, so there's a roadmap for myself, for this project, and also for the nftables space. So For this project, I think we would need a higher level abstraction, but without becoming something like Firewall D, because Firewall D really is an abstraction on top of IP tables and NF tables. Now, people told me my library at times is quite complicated to use, because if you have Boolean expressions like TCP dport 25 or TCP dport 587, that is a Boolean expression, so you have giant trees of these expressions that could be made much easier. I would want to derive a JSON schema for NF tables that everybody could use for any kind of programming language. And another idea that I had is for a comprehensive test suite that will show all of the errors you can make to do some fuzzing of NF tables. So the idea here is to create a large set of NF tables test data that is valid, that is usable with NF tables, and use that for NF tables RS or any other kind of implementation in other languages. So if your library crashes or isn't able to generate this test in NF tables, then it's not correct, obviously. So some resources for you. I can really recommend the NF tables wiki. They have a 10-minute reference. You have NF tables on your system probably, so you can learn it. It's always great to know about the net filter hooks. It's the same for IP tables and NF tables. So there's a giant diagram of how a packet flows through your system with the input hook, the output hook, and so on. The NF tables JSON man page is great, actually, and I think required to use the JSON API even with something like NF tables RS. And also, I can recommend to look at these projects that I mentioned, Netherwark, Wellenbrecher, and how they are doing things. And also, there's BPF, Berkeley Packet Filters, and eBPF. They have a different use case than NF tables. NF tables and IP tables are strictly for packet routing, packet classification, and manipulation. So BPF has other use cases, security software is using it, but they operate at the same layer, so also great to look at that. Yeah, so I can just say build something amazing, try to get comfortable with NF tables because there's value in making things more secure, and that would also require something like NF tables. Any questions? Yeah.
How do you stop Docker stamping all over your changes?
Sorry, come again?
How do you stop Docker from trampling all over your changes?
How do you stop Docker from trampling all over your chains, I guess, IPT? Changes.
So you change something with your automation API.
Mm-hmm.
And then someone restarts Docker, and it reloads all of its network stuff and stamps all over your config.
Yeah, okay, so if you restart Docker, it will kind of undo your changes to the IP tables or NF tables. Yeah, this is a common problem. So with NF tables, you can have different tables, right? So that as I said, a table is very much like a namespace, and so you can have the same hook, like all packets on the input hook should go to this chain in this table. You can have this per table, and it would be quite easy with NF tables to just use, you put your own rules, your own packet rules into another table, not the same that Docker is using. So with Podman, they use Netherwark. It's very different from how Docker works with IP tables, and I think Docker would benefit from adopting something like Netherwark and using NF tables directly. Any more questions? Okay, then you are relieved. It's time for get together. Thank you very much for being here, and have a great day on Config Management Camp.